Hello, 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 Justin. Hello. Oh, thank you. Hello, Kim. Good, thank you. How are you? Hello, Sarah. Hello, Sheeran. Hello, hello, Aaron. Hello, Armand. Armin. Hello, Rachel. Hello, Andre. Hello, Marissa. Oh, right. Yes. Hello, Heaven. Hello, Alea. Hello, Alinele. Hello, Rachel. Hello, Heaven. Yes, good morning, Heaven. Thank you. Hello, Andre. Hello, Erica. I think that's okay. All right. And hello, Erica. Thank you. Um, yeah, I keep saying this, but I know each time we do this, like, hello, oh, wait, more people are here. All right. Okay, hello, hello, Wen Yi. Hello, we'll be having this. Okay, yeah. So this whole hello thing, which I really appreciate, I really do. And each time we do it, and it gets more intense each time. But this like direct, personal, like hello, hello, me, you. Whether you do it in the chat or you do it with your voice or your video. Like, let me just say again, each time we do. Oh wait, someone else is here, I think, or maybe not. But hello, Wendy. Hello, Abby. um, each time we do it, I just want you to know, I find it incredibly awkward. Like I find it very difficult. And each time we up the stakes and we make it more personal, I definitely find it awkward. And I'm sure many of you do too. And that's why I keep doing it. And that's why I keep upping the game on all of us, including me, because the more awkward it is each time to literally say hello to each of you as a person, the more I realize how freaking necessary this whole thing is. Like maybe I've said this already, but like as hard as school was, man, and it was hard to be at school in the day for all of you, for me, like as stressful as it was to be at school. God, it's harder not to be at school, I think. So these like hellos make it that much more real for me, but it also shows how fake all of this is, and that's why I think it's hard. And I really appreciate the goodbyes too. I'm now realizing the funny thing with the goodbyes is the goodbyes are really awkward because by the time you say goodbye to me, if you're like goodbye and then you sign off, then like I literally, of course, can't say goodbye to you. So, but there you get your, I guess that's the revenge moment. I don't know. Anyway, so thank you for saying hello. You're all here. That's cool. Um, um, and it's not to check up on you, I promise. I'm just saying hello to who. I'm not thinking about who's not here. I'm just thinking about who's ever here, which is the point. Okay, so we're going to go back to business. Wait, I think, yeah. Yeah, we're back to this. Homework wise and stuff. Oh, okay. One thing with this class. Okay, so I was up to date with you guys as of about 3 days ago. Like whatever any of you had turned in as of like Sunday night or something, I think I had totally turned back. And also, you may, if ever you see a slightly different handwriting or typing on your homework, on the regular homework, if it looks at all different from mine, yeah, that is Professor Lou for sure. And you know, she's doing what she can on some of the homeworks. And but everything is passing through the system just for what it's worth. Like you can tell, like the nature of Google Classroom, like nothing gets back to you without me fully seeing it, and for whatever that's worth. And really, I'm the one putting the numbers on them too, to tell you the truth. So anyway, but if you handed anything in the like the last 2 or 3 days, then I might not have gotten it back to you yet, and that's on me. Then the ball's in my court now, and I apologize or I thank you for your patience. But I think it's about that. I think I'm about like a day or two behind. One thing I did notice on Sunday, in this, for some reason, in this section, I don't think I've gotten the. Oh, we does. Oh, oh, good point. Thank you, Erin. Oh my God. Okay. That's like really helpful. Of course, that makes sense. I totally didn't think of that. I'm very glad. And I never know what's going on your end. Okay. Sorry. Hold on. Someone else is coming in. Thank you, Erin. Seriously. And again, not to be cheesy, but since we are all allowed to care about our grades, so let me just cheeseophilely say again, like the thing that Erin just put in the chat, even though it has everything to do with the class and not to do with like an equation, she really should triple dip that, or like whatever game turns apply to whatever. Erin, just know that whenever any one of you says a thing like that, or says like, oh, you may, oh, like someone recently caught that I had an ambiguity, a mistake, a confusion that was confusing in the last homework. It's like one of you students, also Professor Lou brought it to my attention, but one of you brought it to my attention. I want you to know, like, you get credit for that. You should grab credit for that. I mean, that's kind of thing, because anyway. So I didn't know that. So it tells you who graded. Okay, good. Well, you guys should know too, though. I didn't even know, even if, so just so you know too, I'm seeing everything. Like it all looks like my work to me. So if something were crazy were to happen on one of your homeworks, so I was like, what? Wait, that's not, I would see it and I would talk to Professor Lou or vice versa, just so you know. Okay. But I do think in this group, especially after today now maybe I've been dragging my heels a little bit, but for some reason I sent a slightly different message to the two different Physics 204 lecture groups. So it's on me, but it is time to really try with that math methods homework. Like as of a few days ago, very few of you had turned it in. It definitely, no one's gonna be marked late, but it definitely is time now. Because as you may have seen, even a third homework did get put in. And if you felt incontinent, no, if you felt insecure about any of this material, but so now it's still fair. I think hopefully I'm going to clear up a lot today. Like, in fact, I'm going to start really getting to the math methods homework today. That should not stop you from turning it in. It should make it easier for you to turn it in, and please do. It's kind of, and don't try to skip to number 3 from number 2. But like, it definitely is time for number 2. Okay, for whatever that's worth. All right, like, don't upset Professor Lou is really what I'm saying. No, that's totally not what I'm saying. Wait, okay, but someone just came and left. Okay, but what I'm gonna spend one more page summarizing where I think we are, because what we've really done is actually a lot of math. I mean, I know it seems that way, but we actually have covered a lot of math ground as physicists here. So I want to summarize it all, say where we are, and then you'll see how it's, and then we're going to start applying it to the homework sheets and to physics. So where we are, like, and this is really what I called finding number 2 on Monday, I believe. Like I had finding number 1, and then we ended with finding number 2. This is all expansion of, like, there's no finding 3 or something. What I'm saying is, if you follow what we were doing with X's, like we started with X's and K's and M's, we started concretely with a physical question of like an actual hunk of material on a spring. I mean, it was in our minds, but it was also in your labs if we didn't have COVID. But like, we're supposed to be imagining an actual object in the real world going back and forth on a spring. And we wrote down some laws about that. Oh, sorry. Totally cool. No, okay, fair enough. I'm getting a couple of. Sorry, one second.
Professor, one of the students asked if you could let her in from the waiting room.
Oh, okay, yeah, wait, yes, thank you, except I don't think I do see, wait, I thought I was trying to let someone, wait, you're right, I mean, thank you. Wait, I'm sounding defensive because I am, oh, there she is. All right, sorry, thank you. Okay, and also someone's in the chat, so bear with me for a second. Okay, wait, I just got a couple of things in the private chat. I'm not going to name any totally reasonable things in the private chat. I just want to share everybody. So this, and it was a couple of people, it wasn't just one, and it was the same message. And like, just want to echo, I don't mean to chastise anybody for, nobody's late on the homework. I'm really not trying to say that. And I'm also trying to say, I think this material is really hard. That is why I take a long time with it, like so long that maybe you're not able to do the homework yet. Like, and it is very possible also that a lot of people in the other class, to be totally blunt, like, they may have either for some reason gotten more scared of me and then like cheated their way through a little bit more. Like, I'm not, what I really want to know from people, honestly, by the end, I will let you know when I think something's late. Like, oh no, okay, here, actually, so that you guys can really read me, I'll say this. I actually do think there's like 3 or 4 people in the class that have not turned in homework 1. Now, I'm still not going to mark that late, but I will say, okay, with homework 1, like, I think you want to start like looking at that and see, like, if you can't do homework 1, then there is some catch up that needs to happen, and either talk to me or whatever. Like, it's not a threat, but like with homework 1, I would say there's maybe a little flag. Homework 2, no, I'm not trying to flag anybody at all, but I still think it would be, I don't think I could do the homework yet if I were in your position, honestly. But by the end of today, I want to know from people, like, not about the homework, but just like, maybe even when there's 20 minutes left, I want you guys to pay attention, and somebody sort of like really like glance at the homework and tell me if what I'm saying seems connected enough to start clarifying now. Like, that's my goal by the end of today. And I mean that honestly to everybody. By the end of today, hopefully there's enough clarity that you could do the homework, maybe not get it all right, but like that you wouldn't feel like it was gibberish. So let me know, like, with about 20 minutes left of today, whether you feel like you might be in a position, you know, because that's my job, that's my goal for today, but I can drift, as you all know. So we'll try not to. So here's what I'm saying we've established. So that's totally fair, what's in the chat. And also if there's somebody else waiting, wait, sorry. I hope that addresses what's in the chat. Oh, okay. No, yeah, totally. Totally. No, like if we all do our job right in this class by the end, we won't all have necessarily learned a bajillion topics, but the things we will have learned, we will really get, and they will be actually deep mathy things that hold everybody else in the world back. Like if we, that's, I mean, these things, and we're not meant to have gotten them yet. We're meant to be getting them together, all of it. Like, okay, but like, look at it. I mean, my God, even to me, it looks like gibberish sometimes. And then I'm like totally psyched. I do understand it. But like, so here's what we started in the class on Thing on a Spring. We were starting by looking at like physical objects, stiff springs with K, heavy masses with M, and they're going back and it's starting at an initial position, X naught, 15 centimeters, right? But then we did a bunch of, like, we looked at Hooke's law and Newton's second law, and we're looking at those K's and those M's and those X's, where X stood for how far the mass is at any moment from equilibrium, like things that seemed reasonable to picture and measure, right? But what's been happening, what I'm trying to sort of emphasize is the mathematical relation that we were forced to deal with by those X's and those K's and those M's. Once we unpack the math enough, we unpacked it mathematically. So now suddenly we're in a position to toss out our X. What I'm saying, our new deal here, and how this ties to the homework and like is that actually the math that we forced ourselves to figure out to understand a mass on a metal coiled spring, like actually, like that math would apply to, like the math doesn't know the physics. So the math doesn't care, first of all, what our X stood for. It just knows how to deal with X. Second of all, the math doesn't care if we called it X or we call it Z or something else. So if we back up a minute and we realize, okay, what was special about X? What was the math really doing to X? Well, it was treating X as a dependent variable, right? And what we had this like back, oh no, sorry. From last week, we had like d to x over dt squared equals negative k over mx. Like, all right, just to remind you where, I think you know, like we had x's in it originally. What the x's were doing was they were being treated as the dependent variable, whereas time was absolutely assumed to be, or treated to be the independent variable. And I'm going to continue to do that. Like I'm going to continue to keep my t, lowercase t there, meaning time. But I'm saying now, if our math was right when we were describing a mass going back and forth on a spring throughout some linear distances, well, if the math was right, then the math was right. And X could have stood for any measurement we could make in the whole world, any measurement. It could be a linear distance measurement, or like as in your second lab, perhaps it could be an angular distance kind of measurement, an angular position measurement. Or it turns out, if we really believe the math, if math is math, like 2 + 2 = 4, it doesn't matter whether it's 2 apples plus 2 apples equals 4 apples, or 2 oranges plus 2 oranges equals, right? The point is the math is not tied to specific objects. So whether we measured a linear distance or an angular distance, or as is going to be coming down the pike, or the strength of an electrostatic field, or a temperature, as homework 3 is a temperature, if we really believe what we're saying and we believe the math, then what we're saying is anytime we find out that some dependent variable, call it Z, anytime we come across a situation where we don't know what the dependent variable is doing something, like anything we want to measure, like anything is a dependent variable. Again, temperature, position, velocity, acceleration, for anything you want to measure. If we have some reason to believe, we don't have knowledge to that it's directly, but we somehow, and this often happens in nature for some reason, instead we have the derivative of the derivative with respect to time of that dependent variable, if we know that the second time derivative of that dependent variable is a linear function of the variable itself. Like, okay, that's what this is really saying. I'm going to actually say it again. Oh, wait, no, I'm not. I'm going to look in the chat for a second. Sorry. What? Sorry, I'm just answering a chat. Sorry, just to make sure everybody's together. Hold on a second. Okay, so I'm saying now, if we ever see a situation where we have knowledge that the second time derivative of the measurement we're making, the variable we're concerned with, the whatever it is. I mean, as long as it's measurable, then thereby it's, as long as it's in science. If whatever quantity we're tracking, if we know that its second time derivative is directly proportional to itself, if its second time derivative is directly proportional to itself and with a negative sign, then, and I'm going to say that again because that is a mouthful, but this is what we're saying. And it turns out to be preposterously powerful. But if we ever have reason to believe, say data-induced reason to believe, or analytical reason to believe, if we believe that the second time derivative of something is directly proportional to itself, to the something, then we automatically know that that thing, that value, that measured quantity, whatever it is, then we automatically know that it is oscillating back and forth, back and forth. First of all, we know it's oscillating. Like I'm saying, first of all, if its second derivative is proportional to itself, if the second derivative is equal to a constant times itself, times a negative sign, but that's still a constant, so I don't really have to say that. If the second derivative is directly proportional to itself, that's what this is saying, then we know that itself, whatever it is, any measurement you can conceive of in any lab, if the second time derivative of that measurement is directly proportional to that measurement, then the measurement is oscillating like co-sinusoidally in time. Like first of all, what we know right away is, oh, that's something that's going back and forth and back and forth. Second of all, we know it's going back and forth harmonically, which means it's going back and forth at a steady rate, at a constant angular frequency, at a back and forth rate, which is steady. And not only is it steady, but we'll right away know exactly what the rate is. The rate will be in radians per second, the rate of the angular frequency. That rate will be the square root of whatever this constant is. That's why we're writing it this way, okay? Like omega squared is just, but that's a huge amount of knowledge right there, honestly. Like we're saying if you ever run into, so in other words, what's really confusing about this is all the squares, honestly. That's what gets everybody, okay? You have to remember that really interesting things do happen when you square a variable, but that's not what's going on here. None of these squares are variables being squared. The squares on the left side are saying second derivative. Okay, there's no, I know we tried to explain that 2 weeks ago, whatever. The left-hand side is a derivative of a derivative. The right-hand side, the omega squared, you got to remember, I'm trying to say to everybody right now, it says this in blue, omega squared is just some constant. Like it's at first, every time your eyes land on that omega squared, there's a moment of deep confusion for all of us because it looks somehow important that it's being squared. But we could have just called it, we literally could have just called it omega, or we could have called it some other letter, like screwed it, we could have called it like omega squared, like made up some weird, like it's, don't think of it as a number being squared, it's just some number, that's all it is. But the reason we're calling it some number squared is with the benefit of hindsight. We're playing Monday morning quarterback, so to speak, even though we're built this way. Like, wait, someone's here, sorry, hold on. We're saying if the second time derivative of some measurement, if the second time derivative, if the derivative with respect to the derivative, I'm sorry, if the derivative of the derivative with respect to time of some measurement is directly proportional to that measurement, then we know the measurement must be oscillating at a steady, co-sinusoidally, at a steady rate harmonically forever. And the steady rate, like what is it? It will be the square root of whatever that freaking constant is. That's what we're saying. So we could have called this thing up here omega, and we could have called this thing down here square root of omega, okay? It's a little confusing that the names went the other way. Omega squared is just some number, but we're saying whatever that number is, if that differential equation is true, then the solution is this. And the angular frequency dictated by this, like this says, it's an oscillator. It's a harmonic oscillator. It's going back and forth at a steady rate. And the steady rate right here, measured in as angular frequency, measured in radians per second, that steady rate must be the square root of whatever the constant was in the differential equation. In other words, if you start with the differential equation, you get this. And frequently, that's actually how it goes in science. Like the data, it's hard to explain always why, but the thing on the spring is case one for us. The data sometimes gives us a differential equation. It doesn't give us a direct function. We get this direct function from the differential equation. And the key thing is knowing that this right here must be the square root of whatever's up there. Like that thing up there won't usually be written as a square. It'll just be some number. What I'm really yelling about right now for all of you is, even if you haven't done homework 2 yet, which you will be in a position to do by the end, but even if you were even to pull out homework 3 right now and just look at it, you'd see that what I'm yelling about right now is like all of homework 3 is just a practice exercise, literally one big exercise in exactly what I'm not yelling at anybody. I'm just yelling out of excitement. Like I'm almost yelling at myself because I'm guilty, because the truth is you could almost do homework 3 right now. You could, based on what I'm saying right here, even if you haven't done homework 2 yet, which is the thing I'm about to go over. But like, if you did have a moment, especially if you're like, he's saying the same thing over and over again. Yeah, I am. I'm totally saying, this is like an old obnoxious joke I used to say, like, why does that teacher say that thing 11 freaking times? Like that teacher says that freaking thing 11 times a day. Like, do you know why? Why? Here's my obnoxious answer as a teacher, as a crusty old teacher. The reason I say something 11 times a day is because I didn't say it 11 times a day. I said it 37 times and you missed it 26. It's so obnoxious. I'm just kidding. Nobody missed it. Anyway, what I'm saying here is this is totally the key to unlock homework 3, even if you didn't homework 2. It's saying whenever you see that differential equation, the square root of that constant, thank you very much. I appreciate that. That square root of that constant is the angular frequency of the harmonic oscillator that differential equation is definitely describing. And now I'll go one step further. The point of Monday was angular frequency, kind of obscure. I mean, in the gut level, it just means how quickly the thing is wiggling, the rate of rapidity at which the thing is cycling. Specifically, it's measured in radians per second, omega. So all you have to just always remember is that there's basically 6 radians to a cycle, like 2 pi radians to a cycle, right? So if you get the angular frequency from the math, then you immediately say, the angular frequency in radians per second can be divided by 2 pi, like because every 2 pi radians is 1 cycle. So whatever they told me in radians, if I want to relate to it, I could divide by 2 pi. That's a standard frequency. Then I'm knowing how many cycles the thing is making per second. And every cycle per second is actually called a hertz. So now I have its standard frequency in hertz. But then if I want to even relate even better, or if I want to talk about what's easiest to measure in the lab or infer or observe, I flip that and I say, oh, it's not, this thing is making 100 cycles per second. So actually what's happening is each one of those cycles takes 1/100th of a second to endure. So the period for this thing is 1/100th second. All of that interchangeable information that just came from omega, and omega is always the square root of the constant in this linear differential equation. So that's like where we are right now. I'm like yelling. I don't know why, because I love the math so much. I really do. Hold on. And I used to hate it. That's why I love it now, because I love the fact that I don't hate it. And also because it's great. Wait, sorry, hold on. Where? Oh, thank you. Okay. No problem. Oh, no problem. Okay. So I think, so I'm going to move on a little. I'm not even going to, I mean, if there are any questions, I'll totally take them, but I'm going to what I'm actually going to do now, I think we can literally, I just died. Did I just die? Wait, are you still there? Hold on. Did I just lose? Wait, wacky things are happening on my computer. Excuse me. My connection to my higher power is unstable. Wait, are you guys you're all okay? You can hear me and see. Okay, you're good. Okay, I don't know why. Okay,
It looks fine.
okay, thank you. Okay, I'm not sure why. Okay, good. All right, sorry. Then I think, unless I'm mistaken, I think we can literally turn finally to homework sheet 2, the math methods. Again, for some of you have been waiting forever to finally go over this. Maybe some of you haven't done it yet. It's okay. We're going to do it together now. I'm going to start going over it now. But I want everybody to stay with me, whether you did it or not. Please. And if you did it, obviously you're just writing down whether you know how to follow. So we're going to do this together. But then for those of you who haven't done it yet, which I do think is still a lot of you, you're welcome to when you turn it in, you're responsible for everything. You can totally use, if we get through problem 1 here today, start with you copying your notes from homework 1. It's totally fine. It's not a question that you had to make this up, but hopefully you use that to then understand how to do the rest, if you know what I mean. Just be honest, but just don't write things that you don't understand. You don't have to make them up to write them. You have to understand to write them. But anyway, so we're going to go over homework 2, and bear with me for a second. I'm going to get it out as well. Yes, you're still okay. Yeah, so homework 2 methods, or even if someone beats me to it, and no, you probably can't share a screen that fast. All right, hold on one second. Oh, wait, I owe this entire class a major apology. I'm sorry. Hold on one sec. I mean, we are doing exactly what I said, but I do owe you an apology. No, my bad entirely. I must say, so mathematical, I haven't shared it yet, but it's up on my screen now. Hopefully you have it too. I mean, because I'll be sharing sharing. I hate that word so much. I mean, on the screen, I'm going to continue to take notes, like always, and doing the solutions out on notes. So I won't be sharing, so to speak, the screen with the question. So hopefully you all have the questions in front of you, or if there's a clever way that you want me to do both, or one of you has, like if we could share two screens simultaneously. Actually, can we do that? Wait a minute. Wait a minute. I'm just curious. Okay, I'm going to start in a minute. I'm going to start doing solutions out to this. I just hit a setting that says you're allowed to share a screen as well. I'd be curious if one of you wants to just share a screen with the questions, and I wonder how this will work if it allows you. If it doesn't, then don't worry about it. But also I owe you all an apology, because I totally lost track of time. I thought I was in the other section right now. Everything I said is reversed. You're the section that totally did hand in. Oh my God. You're the section that totally did hand in math methods a while ago. And hopefully you didn't cheat. So it's actually the other section that's completely behind on that. Although again, everything I said is true. Like if you haven't handed in yet, you're still not behind and you're still blah, blah, blah. But actually I got the two sections for whatever it's worth. No, most of you have handed this in and hopefully gotten it back. So sorry. Yeah, I know someone's going under the bus now. And it's me. Like, what do they say? If you find yourself in a hole that keeps getting deeper and deeper, like, what should you do? And the answer is stop freaking digging. Right. So I'm sorry. This is totally on. I'm so embarrassed. I'm just going to like start going over this homework now. Oh my God. Everybody hates everybody. Oh my God. Really, wait, if I just had A's to give right now, I would really. If I had the wisdom, I would. But okay, math methods too. If anybody wants to share a screen with the questions, that would be great. But if not, here we go. But please do answer questions as we go, or tell. But especially, okay, now in seriousness, since you guys did do this and you got it back, it's very possible that I'm going to go slower than you want, and I do not actually wish to do that. So maybe I'll just start by writing, and you'll tell me if. I'm so going to hell for everything I just said about the other class and you. I don't even know who I feel more guilty about, what I just said to you or what I. But yeah, I mean, please feel free, report me to some kind of higher authorities for that one. But I think the best thing for me to do is keep dwelling on it. I think that will really help. Actually, that's certainly. And you know what they also say? They say cleverness. Cleverness is knowing that a tomato is a fruit, not a vegetable. But wisdom is knowing never to put a tomato in a fruit salad. Okay, so this is number one. Oh, yeah. Oh, sorry. Okay. I'm just gonna pause there for a second. Like these are my answers. And this is sort of the way I would want you. I mean, in principle, I should have started with a diagram actually, but a little abstract here. But this is more or less what I'd want yours to look like, or it did look like. And this is like the nugget of the point, right? So this is going forwards like we did in class. This is like you guess something, but then you're checking, oh, is it, does that equation, that cosinusoidal behavior, describe behavior that satisfies that differential equation? And we're saying yes. Like just like the model that we're now going to compare everything to. So I feel like that's what we've now done like 4 days in a row or something in a way. Is that, so that's A and B. Is that clear? I'm looking, is that, oh, chat. Hold on a second. Oh, no. Oh, no, sorry. So, oh, okay. I'm glad it's clear. Wait, no, I love, wait, no, I'm, oh, no, I'm totally psyched with Marissa's question. No, I don't, I'd love it for the be more you and less me. Absolutely. And I'm not in a rush. I don't need to be, I'm just like always worried about boring people or something. So wait, hold on. So, oh, good. No, and if this is clear, and in fact, I really am meaning to turn it more to you guys. I guess just because this first one to me is sort of like the model, like this is like kind of the summary of what, we've been doing or to show that the homework is connected to class or whatever. I feel like this is what we were doing for days in class. And then now in the back of our mind, what we're watching is like, can we handle this? Like, do we get what this means? Do we get how, what it means to be a solution? And are we clear on that? Even if someone secretly replaced the X's with Z's, like, would that not throw us off or, or something like, but now I'll turn it to you guys. Right now, good, but I'm glad it's clear. Okay. So now I'll turn it to you guys for like part B. It starts getting slight. So now we're going to play with this idea, right? And we're still playing more mathematically than physically, but sorry, B, the one is, sorry, that was B. I mean, now C, sorry. Now C, like, C is asking the exact same type of thing, but now it's sort of, this is like playing scales on the piano and then you're being asked to like now go to a chord or play them faster. Cause like now it's like the same question, but it's not breaking it into steps for us, but it's sort of assuming, and this is what's going to happen through the rest of the homework on the other one. It's like assuming now that we get it and that we get the steps. So even though it's not spelling it out, I'm going to follow the same steps to check, right? But I think we're all going to find, do we all agree the answer to this one to C? Like, I'm going to do it out. Well, no, I'll ask you. I'm sorry. No, Marissa's got to go. Like, do you guys, ultimately, do you think the answer is yes or no to C? And I'll look at the chat. Sorry. I'm totally distracted by something. I think it's called my personality. Wait. Oh, right. Okay. Totally agree. Sorry. I got so I'm looking at, oh, wait. Oh, okay. Sorry. I fell behind the chat, but yes, cool. Sorry. No, yes, good. And yes, I agree that was the private chat people, but yeah, right. Oh, that's interesting. Okay. Well, here's what I want to say. I mean, to keep things rolling, okay, cool. Oh no, and keep it going. Sorry. There's good chat here. I don't mean to cut anybody off. Like, even if I agree, that doesn't mean, because like Yaverbaum has raised an interesting point. So like, even if everybody agree, and it doesn't necessarily well, I think technically it does actually disagree with Marissa, but there's, okay. And I'm now seeing things in the private chat too. This is like so mystical. So anybody else? So anybody wants to say anything privately or publicly? I'm just going to pause for another. So we are going to go through the procedure. The idea is it's the same test, the same procedure as question one, but we're predicting what our ultimate finding is. Is it a solution or not? Okay. Well, yes. Okay. Good point. So now we're getting complex answers. We're getting like yes or no, or it depends on this, or it depends on that. So clearly this is, and by the way, this really is worth, because for the rest of it, see, the thing about differential equations that's hard is not the derivatives or the equations, but they are reverse engineering. What we're used to is like we get something and then we plug it into an equation, or we're asked a question and we have to come up with the answer. Here with differential equations, it's much more like Jeopardy, like the show Jeopardy. It's like you're given a differential equation and the question is blah, blah, blah a solution or not? Like that's how we approach differential equations. Like we look for solutions for them by trying out ones and then asking, does this work or not? So it's really important to know. So that means sometimes they do and sometimes they don't. So it's really important to know what the difference looks like. And that's why we're pausing on this. But okay, so hold on. So, oh yeah, okay. Okay, that's very fair. So now at least I'm going to do at least one person in the private chat now. There's enough complexity out here that at least one person in the private chat has now said, wait, can you go back to B? Because now it's looking less clear to me than I thought it was a second ago. And that's a great instinct. Like the minute C starts, like that's what that's why we spend so much time on fundamentals. It's always about fundamentals. So yes, let me go back to B for a second. Like, in fact, yeah, let me like back to B. B, what we're given, and this is the way it goes, like we're given a differential equation that looks like this. And I'm not, and for any of you who think, like I'm going back to B, I'm not going to spell out the whole B again, but I see why someone's asking this. We're given this. Okay. Now, what is that? Like it's an equation, it has a derivative, but so what? Like, what's the intrigue of it? The point is the assumption when we see that is there's a clear dependent variable and a clear independent variable. Like there's an X sitting there, there's a T sitting there, and we're supposed to understand that everything else that we see is a constant, right? So there's like, so it has two variables that we as scientists are interested in as physicists. But what we always want as a physicist is the dependent variable as a function of the independent, right? We want to unpack this thing. I know you know all that, right? But so that's what we were given. And now we were conjecturing in part B. We were just doing the same thing we did in class, but we're conjecturing a solution that looks like, that looks like this. And now it's our job, what it's asking you to be is to test whether that conjecture is correct or not. So we test it by, we took derivatives, and I'm not going to repeat that part, but we took the two derivatives, and then we took the second. Here's the key that everybody, this is worth seeing a million times because there's a step in here that's really easy to miss unless one practices it oneself, which is that when we took two derivatives, on that second derivative, we ended up getting this expression. And that in itself doesn't really say anything, like what, so what? But I look at that expression and I rearrange it a little bit. I say, well, multiplication is commutative. So I could write it, So I could write it like this. Okay. And when I do that, I realize, oh, I see what happened. When I took two derivatives, when I took two derivatives of this particular X expression here, I ended up with that same X expression down here, but multiplied by a constant and multiplied by a negative sign, right? Like when I took two derivatives of X, I got back X times a particular constant, happens to be a constant called constant squared, but don't let that bother you. Like what we have here is X times omega squared times a negative sign. And that was what we were looking to get. Like that was the quest. Can you come up with an X such that when you differentiate it twice, you get back itself times this constant times a negative sign? And we did. So we say, yes, our X worked. I mean, right. So at least for the one, now I'm going to go to C. I mean, hopefully, so one person just said, can you and this is always the right thing to do. Like when we don't know something, we have to go back to what we do know and spell out even more detail in our own brains, how we knew the thing that we did know. And then we graft that on whatever we don't know, right? So it's really good that the person asked me to go back over B again. So I hope that worked. So now I'm going to go, good. Great. Thank you. And thank you for saying so. I appreciate it. Okay. So now I'm going to go back to C and do that same test and see. And of course, if it always works, I'm doing something wrong, right? Like then it isn't a test of anything. Like hopefully we're going to see some compare and contrast here. And that's why we are playing with it. So if I go to C now, sorry. And by the way, I also see in the private chat, oh, very good. Yeah, I agree. That's good, Yabo. I see that too. And yeah, and good man to be able to recognize. Yeah, but yes, cool. But all right, so here we go. Blah, 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 C. So C, what was given here, sorry, what was given was a differential equation, a second order differential equation that certainly seemed to have that kind of form that we're very interested in now. And that form is, sorry, it was a 3, yeah. All right, so now we're just getting more specific. We're like, okay, let's stop with all the abstractions of omega. Like omega is just supposed to be some constant. Let's make it just some constant number and be concrete about this. So, okay, we've got the second order differential equation given. The question is, well, okay. The conjecture now is something that seems reasonable. Like it seems like, oh, a cosine function again with some kind of amplitude, which is not specified. And following the same pattern, we like put an actual number there for omega. So it seems like, so there's something very reasonable about testing this. Like this is a very reasonable conjecture and it's worth testing. So now we test. And I do agree with all of you. The bulk of you who said, no, this does not work. You're right. Not because we subject it to a different test, but because we subject it to the same test and it fails the test, which is that we take a derivative. Maybe I should be asking you guys this, but yes, I totally agree with those of you who said, so we take the first derivative and we get negative 5a sine of 5t. And then we take, because that's chain rule, right? And then we take the second derivative, chain rule again. So the 5 comes out again, but the negative sign stays because, and the a does not get squared, right? Because the a was always just sitting there. So we get this. So now this is looking good. Okay. So now this is looking like something like, what did we do at this point last time? Well, last time we did a quick rearrangement also. We said like, oh no, we've already done the rearrangement, sorry. So we look at that and then we say, oh, like that's x, so that's good. So apparently what we got was, oh, negative 2 dx dt squared equals negative 25 x, right? And that's great, except that the original question was, can we get d2x dt squared equals negative 3x? And that's not what we got. Like, it seems dumb, but like, this is just the whole point. Like, very close, seemed reasonable, had the right form, but it didn't arrange the constants properly. So this doesn't work because 25 does not equal 3. I mean, that simply. So that, but the importance of this case is it shows, okay, like some things, like just because you have a differential equation doesn't mean that anything you write down is a solution. And even if you're smart enough to have cosine and have units arranged properly, like some things are solutions and some things aren't. So we don't know until we know. Wait, I've just lost the whole. Wait, sorry. So that's C as far as I'm concerned. Oh, good. Okay. Oh, good. Okay. So that's C if there's any. So I say, I agree with you. The answer is no, not a solution. Now D, it puts you through the same thing again. D is kind of redundant now. In fact, D's kind of like, well, it's sort of a check on that. I mean, all right, D is a little bit redundant if you understood C, but it's just sort of checking back on why you believe C. So I'll just do it fast and you'll tell me. Like, so this is like practice, but which is fine. Part of what we're just trying to notice here too is like that cosine functions they come up both because they have that shape, but what we're really saying is, what's the meaning of that shape? The meaning of that shape is this thing, this sort of cycle of derivatives thing that's happening that cosines do properly. Sines do them as well. Tangents don't, right? Just to be clear, like anytime we're doing cosine here, maybe we're about to find, and we will, that sines could have worked as well. But that doesn't mean anything in the world would work. Tangent wouldn't, but anyway, all right, so that's, sorry, so that's D2. All right, so I think that's the answer to D2. Like, please feel free to ask any questions, but I think D is basically the same as, so now I'm going to keep going, if that's okay. Now we're just like we're trying to get fluid between the math and the physics. Here we're reminding ourselves, we're bringing the physics back in sort of, so. Oh, and the Roman numerals, I don't know why the Roman numerals did, but they did. Sorry, it's, yeah, but it did. Okay, that's the first derivative. I'm going to go to the next page. If, oh, wait, if that's okay. Or, well, I'll pause for a second. Sorry. Oh, let me look in the chat. Yeah, yeah, that's right. That's good, Alyssa. Yes, that's right. I mean, that's exactly right. Cool. Okay. Oh, sorry. Wait. Oh, okay. Okay, so that's that. So then the next one. So right, the cool thing about this too is, well, yeah, I mean, it's practice. I don't know what to say. Oh, so that's that one. Oh, chat. Hold on. Oh, cool. Thank you. You're welcome. I mean, okay, so then back to that's three. Right. That's E. I believe that's the end of E. Now, can I scroll? Oh, okay. Now things get a little bit interesting. Things do okay. Now things get a little bit interesting. A little bit. Welcome to my bar mitzvah in F. A little bit, and but certainly, okay. We have a little chord change here in F. So I'm going to ask you in a second. Let me just write it down, and I'll turn it to you guys. So F. And the Roman numeraling is again insane. I have there's no rhyme or reason to it. I apologize. It has, yes, but I'm just going to keep it because there it is. But okay, this I want to turn to you guys for a second. I mean, just to be clear, like, so we're now trying. Well, the 3.5 is a random number. I just want to make that clear. That 3.5 is meant to represent like any random number that could be there. So don't overthink that it's 3.5. It really is meant to be random. But that said, does anybody want to give me the first derivative of that expression? Oh, I'm looking at chat. Sorry. Okay, totally. You guys are fast. Oh, very fast. Two people in the private. Awesome. God, I can't even see, but totally awesome. Yes, I totally agree with the two people that are in the private chat. And they each get a pound of Willy Wonka chocolates and a lifetime supply of gobstoppers and this couch. Yes, I totally agree with two people in the chat that the first derivative, so I'll just write what they said. They said that the first derivative goes like this. In other words, what the two people, sorry. Sorry. And there's more people in the chat. Oh, yes. 3 people in the chat. And again, all of you can submit this for blah, 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 blah. Like, I don't care whether it's private or public at the moment. I mean, and when I say blah, 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 I hope you know exactly what I mean because I don't. Who's the other guy? Wait. Okay, wait. Sorry. Yes, all right. I did go on recording with the chocolate offer, which now means I'm in deep trouble. That is true. And I'm almost afraid. And somebody just put in the private chat something so funny. I don't even know if I can repeat it or not. Hold on one second. Sorry. Now I'm about to get myself seriously in trouble. Wait. Hold on. Okay. Yeah, there's definitely a question in the private chat that is very funny as long as I'm not actually supposed to answer it. But if I am supposed to answer it, I don't know what to do. So back to math. What three people, excuse me, in the three, oh, sorry. Oh my God. Oh wait. Oh wait. No, actually, wait a minute. A lot of math is happening in the private chat now. So right. Right. I want to talk about we do right. So hold on one second. Sorry, one second. Okay. Yes, it's important to realize, like, how do we do this derivative? It's a trigonometric derivative and chain rule. It is chain rule, right? So we do the, you know, the trig thing of cosine becomes negative sine. And I really do want anybody, I'm going to say this is important. And nothing is easy to anybody and everything is easy to everybody once they get it, right? It's like, there's no, but I'm going to say this, but then if you're listening and it's still not clear, please tell me in the private chat, because this can be a holdup and there's no shame. It doesn't need to be, but I'm saying when we do chain rule here, chain rule means take the derivative of the whole inside, like take the derivative of the entire expression inside the parentheses, which used to just be omega t. Now the entire expression is omega t plus 3.5, but 3.5 is a constant and we're taking derivative with respect to t. So the derivative of this whole thing, and we are taking the derivative of the whole thing now, like in other words, I'm respecting the 3.5, like respect, like someone said in the chat, like I am respect, the 3.5 is there and I'm taking a derivative of this entire expression, including the 3.5, but I'm taking dx dt. I'm taking the derivative with respect to time. So the derivative of omega t is omega, and the derivative of 3.5 is 0 because 3.5 is a constant, right? So the derivative that I'm pulling out from the whole thing is still just omega. And this is important. Like, it's not meant to be a trick question. It is meant to be tricky. I mean, but like what we're seeing now, in other words, so if you're with me, if people are with me, I'm saying, yes, I agree with the three people in the private chat that when we take the derivative, the 3.5 stays inside the parentheses because it is still there, but it doesn't come outside of the parentheses the way the omega does. And then when we do that again, I'm just going to do, oh, sorry, that should have been in red. Well, anyway, but if I do it again, now the omega will come out again, just like it always did, but nothing more will come out again. Like it's technically omega plus 0 that's coming out. And the 3.5 is still there. Okay. So now I'm moving ahead here for a second. So this is, so if I take the derivatives of these, so now let me go on the next page. Yeah. So now let's look carefully at this. I'm just rewriting, like it's not a new problem. I'm just saying we started with this. Yeah, so I'm talking here for a second, like this could be for the whole class, but it's like actually not. So this is me for a moment. I'm saying the homework like had some exercises. It was, I think it was getting more clear to people, and it is a little bit repetitive, right? Like we're like practicing this thing in the homework. But now here we are having practiced it. This model of like, you give me a differential equation, I have a conjectured solution, then I test whether that solution actually does satisfy or solve or act as a solution for your differential equation, right? Like that's like the pattern on the table. And now we're given this one. So I'm going to just jump into the pattern. Like, I don't even care what the homework is asking me for the moment, but I'm saying if this is what we were given, a cosine omega that, and we took two derivatives, I'm going to anticipate, like the question is, oh, I mean, this is a whole new kind of function. Like this is, I mean, it's not a new kind of function, but it's a more complicated cosine. Like I never had something in my parentheses before, now I do. So I'm going to ask myself, does this thing satisfy our one and only favorite like differential equation for harmonic oscillation, right? This like that is what like this is the diff EQ for simple harmonic oscillation. So if I ask myself, does this thing satisfy that? Well, it seems like right? I mean, what we just found, like if we look right here on the back page, sorry, we just found that when we took two derivatives of this more complicated cosine thing, because of the way chain rule worked, or because 3.5 is just a constant, like in other words, we just added a constant to our expression. But because of where we added it, and because it was just a constant, apparently it got carried along for the ride in just a nice enough way that like indeed like this whole thing, well, you know, this whole thing with the a in it is x. In other words, in other words, well, I think what I'm trying to say, and I don't mean to jump the gun, but I want this to be uncomplicated. As I mean, I want this to be clear. I am saying yes, right? And now this is important. Like, so I'm saying I don't even know if the homework asked it or not, but the reason the homework just introduced this extra term is to show, oh, wait a minute now. This cosine thing that we've been saying is the description, it's the equation of motion for a harmonic oscillator. Like we've been saying that's how to describe a harmonic oscillator because it solves the differential equation because it's a solution. What this is now saying is, yeah, I guess it was, but it wasn't the only solution. Apparently, we can make a cosine function even more complicated and still be describing this thing. Like apparently we're allowed to add a constant, whereas before we were just assuming it was zero in effect. What we're saying apparently we have more choices here. We can write down a cosine function that has a plus something, and the something need not be zero, and we still are apparently describing a physical harmonic oscillator, which means this 3.5, this constant, has to describe something real and physical. It has to have physical meaning. Okay, to summarize, this is what I'm saying. So, oh, sorry. Yes. Oh, good. I see this in the chat, Holmesy. Yes. So someone just put in the, so this is correct. This is good. And I'm going to keep going for it. But yes, someone just put in the chat, is a 3.5, like by putting 3.5 rather than zero, you just change the starting point, right, Yaverbaum? And yes, like that's very good that someone just put that there by changing well, yeah, I'm going to start writing in a second, but by changing 0 to 3.5, I've in effect changed nothing but the starting point. And that is a very good thing to say because that's why this makes sense that it should still work. It's still the same oscillator. It's still going to go back and forth the same number of times, but starting different place. Only thing I want to say to everybody, I mean, exactly where I was about to go with this is, yes, it's changing the starting point as long as by starting point, we mean starting point measured in radians, because this 3.5 better be measured in radians because it's in the cosine argument. So by starting point, we mean where you start in the cycle. And that is totally right. Like, and actually somebody in the private chat just saved us a lot of time because I don't actually think I have to, so I'm going to write that down. But yes, the 3.5 is a starting point. That's exactly what it is, but it's a starting point vis-a-vis with respect to cycle. That 3.5 is, well, okay. So hold on. Okay, so to summarize what we're saying right now, 3.5 just represent like whatever happened to 3.5 would have happened to any number we put there. And what happened was it didn't change the correctness of that solution. We could put any number we want there, whether like up until now we had been assuming that that number was 0. Now we're saying we don't have to restrict ourselves to that. It could be any number at all, as long as it's a number of radians. Like omega times t is measured in radians because omega is radians per second times seconds. And you can only add apples to apples and oranges to oranges, and you can only add radians to radians. So phi, so this lowercase letter is the Greek. This is a lowercase version of the Greek letter phi, which some people pronounce phi, and nobody actually does know how to. Anyway, you can pronounce it any way you want in this class. What we're saying now is even if you include a constant there measuring in radians, you're still describing a simple harmonic oscillator. So what do you change when you change that constant? When you change it from 0 to something else, what you're doing is exactly what somebody said in the chat. You're changing where the thing begins, but that means where it begins measured in radians. That means where it begins relative to the cycle. So for example, if you started something midway, oh, sorry, I'm sorry. Yes, please go. I'm sorry. Yes. Or someone, oh wait, did someone? Is it Yabo? Question? Or,
My bad, I just farted.
oh, okay, cool. Okay. Oh, good. Okay. So oh, yeah. So if, oh, so say you want to start something midway in its cycle. What do I even mean midway? Like, well, we've been traditionally assuming it all goes back to thing on a spring. Like we've always been figuring that something starts with a velocity of 0 at something we call an amplitude position or an initial position, right? As far away, we've been picturing situations where something starts as far away from equilibrium as possible. And then goes all the way to equilibrium, past equilibrium to the other side, and then back around again. And one cycle means all the way there and all the way back, right? So if we imagine, instead of starting the timing right there, if we, for example, imagine starting the timing when the thing's already over here, when it's already halfway through its journey, then that would be half a cycle. Like if it's there, but it's not back yet, that would be half a cycle. And we would call phi, when we'd say phi is equal to pi, because there's 2 pi radians. Let me just write that down, sorry. Okay, so just quick. So again, just to confirm what someone put in the private chat, and which is right, like that phi represents where you start relative to a cycle. So if where you start timing, So if you started timing when the thing had just gotten to the equilibrium position, like that's like a quarter of the cycle way through, right? Like you get to equilibrium, then you get to the other side, then you get back to equilibrium, then you get back to the original. It's like 4 quarters if you think of it that way. So if you started timing a quarter way into the cycle, then you would set phi equal to pi over 2, because that's a quarter of 2 pi radians, and 2 pi radians makes a cycle. And also, by the way, in terms of what the person said in direct chat, like I'm calling this a head start, you could just as easily call it a delay, and you just have to assign your positive or negative sign appropriately. Like any of these examples I'm giving, it could be a positive or a negative. But I think I'm going to assume that everybody sort of gets this for it. But this means now, oh, wait a second. Now we're going to want to sometimes take into account whether things have head starts or not. Sometimes they don't. Sometimes we can actually just set our timing accordingly. But there are certain cases you'll see where we have to track this. So that's what we just found now, that in other words, this cosine omega t thing was a particular solution we're now getting a more general solution. We're now seeing we're going to have to pay attention to this other constant called a phase constant. Okay, let me just see what the next question. I think, wait, what time is it? Oh, we have like 8 minutes left. Okay, wait. Oh, it would be great. All right, I'm going to take a plunge here. We've got 8 minutes left. I would like to do one more, assuming that there don't seem to be any burning questions. And we'll end on this next one because this is a whole other, but this is just to show you how these things this starts to become a thingy thing in physics. So I'm going to do one more and we'll end on that. Hopefully they'll, and again, just wherever you are, you guys are rocking on the homework. I'm so sorry. So just, I think any of you, if you've done homework 3, there's nothing more to do for the moment. You're great. But I bet you those of you who have done 2, you're totally ready to do homework 3. I believe, I think. Well, actually, you should tell me. I think we said that you were going to tell me. But okay. Anyway, I'm just going to do quick. Well, what do you think you guys can do? I mean, is this clarifying things at all? I'm afraid to ask at 1:23. Well, let me know privately in the chat in the next 7 minutes if there's something that could still be cleared up. Oh, wait. Oh, no. Okay. Hold on a second. Okay, hold on one second. Okay, hold on a second. Sorry. Yeah, I'm going to do one more. Okay. Yeah, I'm going to totally do the next example very quickly, 5 minutes. Okay, cool. All right, so the next example. Okay, so we're going to quickly consider this now. This one is a new function, right? The one thing I know, this assumes, and I know I have like 2 minutes. This assumes that we do remember something from calculus, which is worth talking about for sure. Just like we assume we know that the derivative of sine is cosine, we assume we know that if y equals e to the x, then dy dx equals e to the x. That's almost, you could almost say that's the definition of e. In a weird way it is. It's not exactly, but like e is that one and only function, which literally is its own derivative. Like, I'm not saying you're supposed to, I'm not saying anybody in the room is supposed to be like, yes, obviously that's true about e at toe. I totally get that. No, like you're supposed to be familiar that it's true, hopefully. Why it's true is a whole deep, fascinating thing that we can or cannot talk about, but I'm not expecting that you're like, you will have accepted that on faith in a certain way if you've learned it in a math class. And that's what we'll do for the moment. But as long as you're comfortable knowing that e is the name of that one and only function, which is its own derivative, then if we do this example quickly in the 3 minutes, if we're considering this, and we know that about e's, and we still have chain rule, like we're also assuming chain rule, then I quickly say, from chain rule, right? I say that, and then from chain, then doing it again, and this is where we're going to end today. I say that, right? I did it a little bit fast, but it's like the negative omega comes out twice. So you not only get omega squared like we're used to, but you get negative times negative. So that becomes a positive. So in the end, we get this. So the final answer to this, I hope everybody sees, like, as to does this, like, in other words, we have 1 minute, or 2 minutes. In other words, we're trying E now. Like we're trying, like, where did E all of a sudden like come into our lives? It came in because we recognize that E has that kind of quality that when you differentiate it, you get back to itself. And remember, that's what we liked about cosine. I mean, cosine, it took 2 steps, but that's what we wanted. We wanted 2 steps, cosine to be get back to itself. That's what the differential equation says. And E does that every step. So in 2 steps, E should come back to itself. So it seems like worth trying. Like we're trying out the E to the X solution to see if could that be used to describe a harmonic oscillator. And wouldn't it be interesting and curious and weird if it did? Because E functions, if you're familiar with them at all, they're exponential. They either like go up or they go up or they go down or they go down, but they don't go down and up and down and up and up. So it certainly would be curious if an E function could be used to describe this harmonic oscillator. And indeed right now, but on the other hand, it would be curious, it would be if an E didn't help at all, because E does have that quality about differentiating. What we find here, and this is exactly where we're ending, sorry, is that, oh, close but no cigar. Like E did do something right, but with the negative signs, it played differently from the way cosine and sine do. So something is different just enough that what we don't get, we get a differential equation. I mean, for sure, don't make no mistake. We do get this differential equation. That is a differential equation, but that's not the one we started with. That's not the one that describes harmonic oscillation. Like if that's physics, it's some other physics, not this physics. So this E function, this is where any fails, like it does not satisfy. So that's, I'm good. Okay, so it's 120. So I'm going to pause if there's any, let me look in the chat. Oh, yeah. Yeah. Wait. Sorry. Yeah. And we're totally, so there's a question in the chat. Yeah. I mean, so what the thing is, it turns out you'll see a couple steps later, and we're going to go over this in class. It turns out when I say E is close, but no cigar, like there's a way of getting the cigar. There's a way of using E. If you throw in an I, as some of you saw later in the homework, if you throw in I for some very strange, reason, then you can, it does work. And it's true that whenever you mix exponentials with complex, with imaginary numbers, well, if you mix them the right way, you get trigonometric functions and vice versa. That's a very deep, weird thing. It doesn't mean you have to always do that in physics. I'm just answering a question in direct chat. I'm not saying in physics you always have to use imaginaries or exponentials if you don't want, but I'm saying you can. Whenever you could use a cosine, it turns out, and again, this is just jumping ahead, this is what we're going to see, but whenever you could use a cosine, you could just as easily use a complex exponential, or vice versa. If you want to use an exponential, you can use a complex cosine. Very unexpected, but we'll see that. We'll see that when we go over them. But yeah, we'll definitely talk about it. So that's a good question. I'll say more, except I know class is over now. So I'm just here to answer any question. If you're good, I'll say like each one of you say goodbye, and then I'm good. But if you have a question, you can hang out for a second. But goodbye. But thank you. I mean, I'm good. I'm just here for questions. Oh, thank you. Thank you, Kimberly. Goodbye. Thank you, Andre. Goodbye.
Hi, Professor. Thank you.
Thank you. Goodbye. All right. Thank you. Cool. Thank you. Bye. Thank you. Awesome. Thank you. Thank you. Thank you, Yabo. Goodbye. That's funny. Goodbye, Yabo. That's good. Okay. Goodbye.